Okay, I'm recording this session. Here I am considering a linear programming problem max z, which is given by x plus 2y. We are going to solve it by big M method. Okay, so max z equals to x plus 2y subject to x plus y. Now I am taking what? Something which has not been taken earlier. I am going to take it as x plus y less than or equal to 2. One is lesser than equal to inequality, and another inequality I am choosing as x plus y greater than or equal to 2. So that xy is greater than or equal to 0, and we want to solve it by big M method. How do you identify that a particular problem will be solved by big M method? If the problem contains greater than inequality, then it will be automatically understood that this problem will be solved by big M method. Only lesser than inequality type of problems uh, can be solved by ordinary simplex method. But if greater than inequality is there, that will indicate the problem will be solved by big M method. Any guess for this solution for this particular problem? If I want to draw this if I want to do this particular problem by graphical method, what will be its solution? Quickly do it in your copy and write in the chat box that this will be the solution of the linear programming problem. Because once I start linear programming problem by simplex method, you can verify that yeah, it is indeed so. Now I'm starting with linear programming problem. So the big M method. So you see, I have to convert this particular problem into in equality type. So in the first inequality, the left hand side is less than the right hand side. So we are going to add a quantity on the left hand side, which you know that is known as a slack variable. So here S1 is a slack variable, remember. And oh sorry, this particular point is 4. I'm considering the same scenario where one inequality is lesser than and another inequality is greater than. But in the second inequality, I'm seeing that the left hand side of the inequality is greater than the right hand side. So I have to subtract something from the left hand side. And once, as I told you, this variable S2 is called the surplus variable, and every surplus variable is associated with artificial variable. Every surplus variable is associated with artificial variable. So we have to add one artificial variable here also, for which the name is actually called artificial variable technique. Yeah, Oritrapal has correctly written that this particular problem has no solution. So this problem has no solution. So we will try to look at it from the viewpoint of simplex method. This is the solution of the problem. Now, since artificial variables are involved, so this particular technique is also known as artificial variable technique. Okay. And the contribution of this slack and surplus variable in the objective function will be 0. So we will write as 0 into S1 and 0 into S2. And the contribution of the artificial variable in the objective function will be capital M, which will be subtracted from the objective function. Here capital M is a hypothetical contribution of the dummy variable A1, in objective function. In objective function. And all these variables are physical variables, so they will be all non-negative. Now, number of variables, in this case you can count them to be 5, and number of equations, here this number of equations, how many equations are there? It is 2. So 5 minus 2 variables, that is 3 variables, will be given 0 value arbitrarily. This thing, when we put 0 value to this variable, this number of variables, this is nothing new. You have done this technique in the transportation problem, that is in modified distribution method, where when we solve the equation Cij equal to x ui plus vj, you did the same thing. How many ui's are there and how many vj's are there? Their sum total minus 1, something you did similar fashion. The same thing you have done over here, because all the transportation problems are actually linear programming problems. You already know it. And by convention, these variables, since 3 variables has to be put value 0, so we shall first consider the original variables, we will put them 0, and then I have to consider the surplus variable. Surplus variables has to be made 0. Otherwise, things may become negative. If I consider, say for example, if you say, no, I will not put S2 0, I will put S1 0. Why not S1? So if I put x equal to 0, y equal to 0, and S1 equal to 0, then that will be, what will you get? You will get 0 equal to 2, which is absurd. If you say, no, I will put x equal to 0, y equal to 0, and A1 equal to 0, then in that case, S2 will be minus 4, which is absurd. So therefore, the convention is first the original and then the surplus. When we put these, after putting these, we get S1 equal to 2 and A1 equal to 4. So it is called these are called the basic variables. These are called the basic variables. We are now going to construct the simplex table in the next page. Can I go to the next page? Can I go to the next page?
Yes, sir.
So simplex table 1. Okay. So the format is Cj, Cb, B, and XB. Now you see, sometimes mistakes the mistakes which I have done by not recording the previous session, sometimes these mistakes are actually good for the system, because the students, the participants who think that they can see my video of the last class in the YouTube, they will not be able to do so because they are absent and the video has not been recorded. So that is the thing. I didn't do it intentionally, but it happened. It's sort of punishment. Now you see, let us put the variables x, y, s1, s2, and a1. Contribution of x1 in the objective function is x. Contribution of x in the objective function is 1. Y's contribution is 2. So, and s1's contribution is 0, s2's contribution is 0, and a1's contribution is minus m. Since the contribution of a1 is minus m, therefore this method is called big M method, since a hypothetical quantity m is involved here. This m may be anything. This m may be 1,000, this m may be 1 lakh, this m may be 100, etc. Anything. It is a hypothetical. Now, what are the basic variables? The basic variables are s1 and a1. So we are going to put it. So we are going to write s1 and a1. What is the contribution of S1? S1 contribution is 0 and A1's contribution is minus M. And what are this matrix? Okay, let us write 1 1 1. Okay. Oh, what are the values of these these are basic variables 2 and 4. So let us put it 2 and 4. And what are these equations? In the equation, the coefficient of the variables are 1 1 1 0 0. So we are going to put it here 1 1 1 0 0. And in the next, there is no slack variable, so the coefficients are 1 1. Slack variable has no coefficient, so it is the 0. And S2 is minus 1, and S2's coefficient is minus 1, A1's coefficient is 1. So we are going to write it as 1 1 0 minus 1 and 1. And the ZJ, the formula of ZJ is, I am again writing, it is CBT in the multiplied by the variable. So it would be 0 into 1 plus minus m into 1, that is minus m. 0 into 1 plus minus m into 1, that is minus m. 0 into 1 plus 0 minus m into 0, that is 0. 0 into 0, that is minus m into minus 1, that is m. 0 into 0 minus m into minus 1, that is minus m. And Zj minus Cj will be minus m minus 1, minus m minus 2, 0, m, 0. Minus m minus 1 and minus m minus 2. Which one is the most negative? I think minus m minus 2 is the most negative. So let us try to see it. If I cancel it, we will get minus 1 greater than minus 2, which implies 1 less than 2. So minus m minus 2 is the most negative number. So we'll put an arrow mark over here, which indicates that this is the pivot column. This is the pivot column, and this variable is the entering variable. This variable is the entering variable. And we have to divide the values of xb by the pivot column. So we are going to write it as 2 by 1, that is 1, and 4 by 1, that is 4. And the minimum positive ratio is 1. And therefore, the variable which will be departing is S1. S1 will depart from the system. And the pivot number is the intersection point of this pivot column and this pivot row, and therefore it would be this one. This is the pivot number. Now you see, in the next phase, I am going to construct the simplex table 2. In the simplex table 2, we are going to write the same matrices. We are going to write the format first. So artificial variable will remain here because it has not become vanished yet from the basis. Okay. So
sir.
yes.
স্যার আপনি আগের বার তো ওখানে ফর্মুলা লিখেছিলেন CJ minus ZJ.
No, ZJ minus CJ always ZJ minus CJ, always, never CJ minus ZJ.
আচ্ছা.
So we have constructed the format this, and you see the variables contribution. Let us put the variables contribution 1 2 0 0 minus 1, and this S1 will be replaced by y, and A1 will remain there, and y contribution of y in the objective function is 2, and it is 0. Okay, now this number is 1, so this position is the pivot position, and we know that the row which contain the pivot number, that row must be written first and in such a way so that the pivot number becomes 1. So actually, if the pivot number is not 1, we divide the entire row by the number itself to make it 1. But here the pivot number is itself 1, So we are going to copy it, or you can say that we are going to divide this row by pivot number 1, which is the same thing. So we are going to write it as 2 1 1. This is the pivot position, earlier pivot position, and 1 0 0. And we construct the remaining rows in such a way so that below the pivot number we get 0. But once, remember, once you construct the new row which contains the pivot number, this old row will not be considered anymore for the calculation. So to calculate the new row, we have to consider the new row which contained the pivot number earlier and the old row which is to be changed. So we can name this old row as R2 old, and we can name this row as R1 new, and the new R2 new can be written by the formula if we subtract R1 new from R2 old. This is the row operation we perform. So we get 4 minus 2, that is 2, 1 minus 1, that is 0, 1 minus 1, that is 0, 0 minus 1, that is minus 1, minus 1 minus 0, that is minus 1, and 1 minus 0, that is 1. Okay. Then again, I'm going to multiply Zj, and I'm going to find out the elements of Zj. So we get 2 into 1 plus 0 into 0, that is 2. 2 into 1 plus 0 into 0, that is 2. 2 into 1 plus 0 into minus 1, that is 2. 2 into 0 plus 0 into minus 1, that is 0. 2 into 0 plus 0 into 1, that is 0. And Zj minus Cj will be 2 minus 1, that is 1. 2 minus 2, that is 0. 2 minus 0, that is 2. 0 minus 0, that is 0. 0 minus minus m, that is plus m, and voila. So you see that in this particular row, all the elements of Zj minus Cj are all positive. All the elements of Zj minus Cj are positive. So this simplex table 2 is my optimal table. Okay. And the theory says, but you see, this artificial in the what we are actually getting from this particular optimal table, what are the values of the variables? What is the value of x in this optimal table? Since x is not present over here, so its value is 0. What is the value of y from this table? Y is present with the value 2. Okay. What is the value of S1 and S2? S1 and S2 both are not present in this basis. So S1 is 0 and S2 is 0. But a artificial variable A1 is present. So its value is 2. So you see that if I am going to substitute these values in the objective function, what will I get? Your Z will become, your max Z will become, or Z max will become 0 plus, what was the max Z? X plus 2y plus 0 into S1 plus 0 into S2 minus m into A1. So we are actually getting 0 plus 4y, 2 into 2, that is 4, plus 0 minus 2m. So we are actually getting 4 minus 2m. But this m is hypothetical. We do not know its value. We do not know what m is. So therefore, algebraically, the solution of the problem is not known to us. Solution of the problem is not known to us. Why? Because artificial variable objective optimality has been reached, but the artificial variable is still present in the basis. If the artificial variable presents in the basis, the optimality solution, the solution has infeasibility. So one can set a question like this: in an LPP, if in the optimal table artificial variable remains present, then number one, the problem has unbounded solution. Number two, the problem has unique solution. Number three, the problem has multiple optimal solution. And number D, the problem has no solution. And you know, since you have done this problem, you know this answer is correct. Another problem they may ask that in an LPP, once artificial variable becomes departing variable, which of the following does not happen? Okay, question number. So slack and surplus variables of the problem have net contribution 0. Number two, the simplex table may not be optimal. Number C, the artificial variable column retains its position in the new table. Which one is correct? The answer is this. Why? Because this is wrong. It is asked that which of the following does not happen. Once the artificial variable becomes departing variable, the artificial variable column doesn't retain its position. It is removed from further analysis. So you see, many more questions can be set from the technicality of the simplex method. And Orithropal had already given us that this particular problem had no solution actually. So let us all verify it quickly, whether it is indeed happening by graphical or not. So you see that if I draw this figure, quickly I'm drawing, this line is what? X by 2 plus y by 2 equal to 1. So suppose I'm choosing my point here as 2 and here it is 2. So this line is the line 1. And here I'm choosing it as 4 and here I'm choosing it as 4. So this line is your line 2. And you see that this is lesser than type inequality. So the region will be this portion. And this is the greater than type of inequality. So region will be that portion. So no common feasible region. no common feasible region, and therefore no solution. And here also in the simplex table we have obtained that there are no solutions. There are no solutions. Another question can be asked from objective question can be asked from this particular simplex method, that in an LPP, if the optimality is reached in a particular simplex table, okay, number one, acha, which of the following is wrong? Optimality is reached, acha, with a solution. With a solution. Optimality can also be reached with no solution, isn't it? So which of the following, acha, okay, optimality is reached with a solution in a particular simplex table, which of the following is wrong? So number one, Zj minus Cj greater than or equal to 0 for all j. Number two, artificial variable remains in the basis. Number three, minimum positive ratio shouldn't have to be considered anymore. And number four, slack or surplus variable may be present in the basis. So the answer will be this one. If the optimality of the simplex table is reached with a solution, then artificial variable shouldn't remain in the basis. Slack can remain in the basis, surplus can remain in the basis, but artificial variable shouldn't remain in the basis. And obviously, if the optimality is reached with a solution, Zj minus Cj is definitely positive, non-negative, so therefore it is optimal. Minimum positive ratio shouldn't have to be, minimum positive ratio is calculated to get the departing variable. And since optimality has already been reached, no departing variable is counted any further. Slack and surplus variable may remain in the basis if optimality is reached. Okay, so you may get a system where the final table, one of the original variable is present and a slack variable is present. This may happen, as in this particular case. Now here it has not been hasn't happened. I cannot cite example right now, but yeah, it can happen. Okay, these things will be clear. You'll be able to reply to MCQ type of questions if you do problems by your own hand, as many problems as you can. Okay, then only the technicality of the thing will be clear to you, and no questions can deter you from answering. No questions will deter you from answering that. Okay, so therefore whenever any problem can be set in any way. So for example, I could have written in an LPP of the optimality which is not happening. The say for example, I can write Zj minus Cj is in an LPP with optimality, Zj minus Cj cannot be less than or equal to 0. So one theory is there. I can twist the theory in any way, and I can present it in front of you. Okay, examiner's main objective is to put the meat in the table, and you are to eat that meat and digest it. That is the thing. He can deform, he can twist in any way the same old thing, but if you are, your vision, your purpose is clear, your technicality, you are clear with the technicalities of the or intricacies of the problem of the theories, nothing can deter you from answering that. Okay, so this is the thing which I wanted to discuss. So if you have any question regarding Simplex, you can ask me, and otherwise I'm going to leave the class right now. In the first session, I showed how to show the particular set is convex set. That video has been recorded. That session has been recorded, and this session has been recorded. Only thing that unbounded part was not recorded. Hope that you can do it. You can again reproduce that thing well. Okay, I actually considered the same problem here. Both the inequalities were greater than type of inequality. If we do so, the solution will become unbounded. In that case, you take it as homework and try to do it by yourself. So this much for today. I'm now pausing my recording at this stage, and if you have any questions,